Good afternoon, everybody. So, we are in the last class of coordination compounds, where we are talking about the complexes and how we can explain their different physical behavior as well as the property. And in terms of valence bond theory as well as the crystal field theory, we are trying to figure out the electronic configuration. So, we all know that how we can have the corresponding electronic configuration, and that the changed electronic configuration in say crystal field, where we see that a metal ion is considered as a positively charged point center and the ligand is slightly bigger negatively charged species, and this particular interaction, when they are forming a coordinate bond, we are considering them as the interaction what we can find in the crystal of the salts like say sodium chloride, and how the different orbitals, particularly the d electron configuration. So, we are looking at the corresponding d electron configurations in the changed condition with regard to the corresponding geometries, which is very important. How we can have a metal complex, whether we have a Ml4 complex or Ml6 complex, what are the corresponding geometries we should all know, and those geometries will also tell us that how many number of unpaired electrons will be there in that particular molecule or the coordination complex, because these number of unpaired electrons which we should have some importance related to their reactivity, catalysis and all these things, which we do not see very much in the corresponding organic chemistry, but the coordination chemistry and the inorganic chemistry of the transition metal ions are largely dominated by the number of unpaired electrons. So, those unpaired electrons have some important role to play, and how we can determine based on this crystal field theory, how we can determine the new n values, that means the number of n values which will be directly related to the corresponding magnetic moment values. So, what we see now that we have 5 d levels or the d orbitals, and we know that in presence of say 6 ligands, their overall energy is elevated, and after that from this value which we consider as the E, which is before the splitting. So, we require something which we consider as the crystal field splitting. So, the splitting will be there, and that splitting will give rise to a doublet state and a triplet state, and these two doublet states and triplet states are separated by say a magnitude of x and a magnitude of y. So, if all of them, that means the available capacity of all the 5 d orbitals, that means we can have the 10 electrons. So, before splitting the energy will be 10 E, and after splitting we see that these are the 2 levels which can occupy 4 electrons. So, it will be 4 into E plus x. So, this will be 4 into E plus x plus 6 into E minus y, 6 into E minus y. So, that basically gives rise to 2x is equivalent to 3y. So, what is the gap? Basically we are looking at this gap from the level E. What is this gap x and what is that gap y? So, this will give you some relationship which is 2x is equal to 3y after splitting. So, on the left hand side we have the before splitting condition, and on the right hand side after splitting, and these two we all know that this is the crystal field splitting. So, this particular crystal field splitting in octahedral geometry, which will be delta O. So, that delta O will be this, and therefore, we get the magnitude of x as and the magnitude of y as 3/5 of delta O and 2/5 of delta O, and if this is also equal to, sometime we also write that is equivalent to 10 dQO. So, will be equal to 6 dQO and will be equal to 4 dQO. These are the magnitude of these separations. So, what we see that we know that this is the T2G level and this is the EG level. So, this T2G level is therefore stabilized by minus 4 dQO. This is the magnitude, the magnitude of y, and the EG level will therefore be destabilized by plus 6 dQO with respect to the unsplit barycenters, with respect to this E level. So, with respect to this, how the splitting can take place, that we can find it out now. Now, the change condition, what we find that we have a new electronic configuration. So, instead of saying that we have a dn electron configuration, that means the number of d electrons in the different levels, it can be 3d, it can be 4d or it can be 5d levels. But now, we will just try to write in this fashion in an octahedral geometry, what are the number in the T2G level and what are the numbers in the EG level. So, we will designate over here the number of electrons in the T2G level, that means the corresponding level which has a threefold degeneracy, and as I told you that G is the corresponding term related to Gerade, which is equivalent to even, and this 2 is coming from a typical C2 operation, because all the d orbitals, why it is even? Because all the d orbitals what we see, they are corresponding orbitals retain or they keep their sign of their wave function same with respect to the operation inversion. So, that is the thing with respect to the inversion which is at the metal ion center. So, that is also important, that how the metal ion is there in the octahedral symmetry. So, symmetry is octahedral. So, all the orbitals, whatever orbitals we are talking about, they all follow the thing that they remain the inverted form and the sign of those orbitals are maintained and they are of even category or Gerade category. So, these particular information will give rise to some other information to us. What we get that the crystal field splitting, which can account for magnetic properties in terms of high spin and low spin complexes. So, these high spin and low spin complexes what we see here is related to the corresponding occupancy of the level T2G and EG. And now, if we just define how we can just go to that particular stage, that some of the ligands will categorize them as weak field ligands and others are high spin. So, weak field ligands are therefore giving rise to the corresponding high spin paramagnetic species. That means, ligands are not changing the corresponding pairing of the levels with respect to the corresponding crystal field splitting. So, we see compared to that, we can have another category of ligands which are strong field ligands, which will be responsible for low spin or rather diamagnetic systems. So, these low spin or diamagnetic systems are very important, because sometimes we find that the metal ion electronic configuration is not immediately giving a low spin configuration of 0 magnetic moment, is typically diamagnetic situation, but through oxidation such as cobalt 2 plus. So, cobalt 2 plus in whatever coordination geometry, whether it is a tetrahedral one or a octahedral one, is not diamagnetic, but once the octahedral species is oxidized for 1 electron, giving rise to the corresponding trivalent cobalt center, we get a diamagnetic situation where the cobalt complexes would be diamagnetic. So, that we will see how it can be applied to a situation where we see that both of them are trivalent cobalt center. In the left hand side, what we see that the fluoride ligands. So, fluoride ligands which is hexafluorocobalt 3 species, and on the right hand side hexacyano-cobalt 3 species. Both of them having charge on the ligands, and both of the complexes are anionic, but the situation is such that on the left hand side our compounds are corresponding compounds are paramagnetic, because if you have 6 electrons to distribute for cobalt 3 plus, and this is the T2G set and the upper two are the EG set, and since the delta is small, so this is the fluoride ligand. We can categorize this fluoride ligand as a weak field ligand. So, this fluoride ligand will be a weak field ligand, and in terms of the corresponding previous definition for the from the valence bond picture, what we have seen that COF6 3 minus having 4 unpaired electron in the 3d6 configuration, that means all the 6 electrons will be paired up, and this can be defined from sp3 d2 hybridization. So, this sp3 d2 type of hybridization will give rise to high spin complexes, whereas for COCN whole 6 3 minus or unpaired electron is 0, which is still 3d6 electronic configuration, and the hybridization is d2 sp3 and is low spin. So, these two levels what we are now bringing is not due to the valence bond picture, but is due to the crystal field picture, because in both these two cases what we have seen that it is 3d6 and it is also 3d6, and until and unless we divide these two into the corresponding T2G set and the EG set, we cannot explain the different number of unpaired electrons for these two cases. So, that we will see here in the case of this high spin and the low spin complexes for the different delta values. So, for the left what we see here is the corresponding value for is less. So, the fluoride ligands are weak field ligands, so that give rise to a very small value of delta, whereas the cyanide ligands giving rise to the strong field for the metal ion, and which having some delta value which is pretty high. So, simply just comparing these delta values, the magnitude of these delta values after crystal field splitting due to the presence of these ligand, we see that the cyanide Cn minus will be a stronger ligand or a strong field ligand compared to fluoride. So, if we take these two examples like that, what we have seen in case of the nickel, that water molecules, the ammonia molecules and ethylene diamine, simply we can talk in terms of the corresponding delta values, and these are deltas O, that means the delta for the octahedral symmetry. So, we can have some leveling for these thing, and we just simply write now that instead of 3d6 electronic configuration for cobalt 3 plus in an octahedral field, if we have a configuration like this, how we can measure the corresponding stabilization due to crystal field splitting, which we consider it as the crystal field splitting energy. So, we will have number of electrons in the T2G level and some other number of electrons in the EG level, and that will now give rise to the corresponding electronic configuration in terms of the crystal field picture. So, the net energy of the configuration relative to the average energy of the orbital is what we have just now calculated, is that minus 0.4 x plus 0.46 y. This we are just calculating it out by 2/5 of delta O and 3/5 of delta O in respect to that delta 0. So, that will give rise to the delta O is 10 dq, and therefore, what we see a situation beyond D3, because D1, D2, D3, 3 electrons will initially be fed into the T2G level. So, there is no such competition for occupying the other level, but when we move to the D4 situation, so the configuration is D4. So, when the configuration is D4 in the weak field condition, so this is the statement, that means in the weak field condition our delta value is less than P. P is nothing but our pairing energy. Whether this fourth electron, when we go beyond D3, whether the fourth electron will come to the T2G level or it will go to the EG level. So, there will be a choice. So, that choice will be dictated by the amount of splitting, whether your delta G0, delta O is appreciable compared to P. If it is higher than P, this electron will come to the lower level, otherwise it will be in the EG level. So, the weak field situation will give rise to something where we have 4 number of electrons in these levels, 3 T2G level and 1 EG level. So, all of them will be unpaired. So, we get a situation which is a high spin situation. But for the strong field ligand, which we just now seen for the cyanide ligand, the cyanide group which is binding to the cobalt 3 center, your delta O is greater than P, is greater than the pairing energy. So, this delta 0 will be higher. So, that is why the fourth electron will come to the T2G level, which is T2G4. So, simply this particular information can give rise to some information related to the electronic configuration. So, if we have a D4 electronic configuration, so that D4 electronic configuration, now we can write what we are just telling, that it will be T2G3 EG1 and another one will be T2G4 only. So, this will be high spin and the other will be low spin, and in terms of the crystal field stabilization energy, if we add up all these things related to the corresponding stabilization of the one level as -4 dq or the corresponding one is 2/5 of delta 0, this will be -3/5 delta O, but in this particular case the E value will be equal to -8/5 delta O plus P. We have to consider this one pairing energy, because in the T2G level we have 3 things. So, this the third electron is going on, all of them are unpaired, but when the fourth electron is coming, it will be paired up in the T2G level. So, we should consider this particular P value for this energy difference. So, these are the 2 energy differences for the high spin and the low spin configuration, and we will see what are the corresponding contributory factors which can dictate us that whether we should have a low spin complex or a high spin complex, depending upon the nature of the corresponding ligand available to us. So, P is therefore the corresponding pairing energy, and when we consider the pairing energy together with the crystal field splitting, what we find that it increases as the ligand varies in some order. Just now what we have seen, that Cn minus is greater than F minus, and previously in case of nickel also we have seen some order. So, if we put these ligands, these 3 we have seen, this H2O, NH3 and En we have seen in case of nickel 2 plus, and in terms of the corresponding equilibrium, the coordination equilibria, we have seen that we can have some order when the nickel is a hexaco complex. If we add ammonia, ammonia molecules will be replacing the water molecules, and afterwards if we put ethylene diamine, that ethylene diamine will also be able to replace the NH3 groups. So, that we have seen in terms of the corresponding coordination equilibria, and that equilibria will tell us that ethylene diamine is a stronger ligand with respect to both water as well as ammonia. Now, we see the magnitudes, so a little bit we are now quantifying the magnitude of the delta, the amount of crystal field splitting. So, that energy is basically changing from left to right, and we are getting all halides, basically 4 halides if we put, then the fluoride is stronger within that particular series of these halides. So, iodide, bromide, chloride and fluoride. So, these things are always be there, and we will find out somewhere that this particular one will also be considering when we talk about a particular oxidation state of the metal ion. If the metal ion center is oxidizing, and if it tries to bind with the iodide one, the iodide ligand, and we should also consider the corresponding ability of these centers to remain as the individual form or they are getting oxidized. If the metal center is oxidizing, so there will be a tendency to oxidize iodide ions to iodine, chloride ions to chlorine. So, that will also lead us the elimination of iodine, bromine or chlorine instead of typical coordination. But when we see that the fluoride is there, and definitely the fluoride is little bit stronger within this particular series, and the fluorine will not be there, that means the any metal ion which are forming the corresponding complexes with fluoride will not be able to oxidize the fluoride ion. So, we see that this particular series, so we can put more and more number of ligand centers. Even in your CBSE book, a huge list of those ligands are there, which are commonly encountered by us, what we commonly use basically, because already we know this the halide groups also, these three we have known, these are known to us with respect to the binding to the nickel 2 plus center, and just now we have seen the corresponding efficacy of this cyanide ion with respect to the fluoride ion when we talk about their coordination to the trivalent cobalt center. So, this particular series or any extended series is known as spectrochemical series. So, from the left to right the ligand strength is increasing, because that will lead us to some greater amount of splitting with respect to the delta values for these ligands covering this particular metal ion. So, on the left hand side the ligands will have the smaller delta values and the right hand side will have the bigger or large delta values. So, the left hand ligands are weak field ligands and right hand ligands are strong field ligands. So, just now the way we have seen how we place those electrons in the different d orbitals. So, after D4 we have a situation where we get a D5 situation. So, D5 situation, the drawing will tell us, you see now how we draw this. Just now we have seen that the delta value is less, we get the high spin situation, and when the delta values is high, we have a low spin situation. So, just changing this particular number of electrons. So, this is a high spin situation for a D5 electronic configuration. So, immediately we should know also that what D5 electronic configuration we know for the corresponding metal ions, whether it is chromium or manganese or iron in a particular oxidation state. So, whether that particular compound will give rise to a corresponding complex which has a very high magnetic moment or a very low magnetic moment having 1 unpaired electron only. Then we have the situation just now what we have seen in case of the cobalt center. So, the cobalt which is trivalent cobalt, and the trivalent cobalt will therefore definitely be considering in terms of these two situations. Unlike the D5 situation, the D5 situation is that 1 unpaired electron and 5 unpaired electron, and in case of D6 it is 0 unpaired electron and 4 unpaired electron. So, 4 electron paramagnetism versus a diamagnetic situation. So, that is a typical drastic condition change, that if we are able to make some compound where we get, that means the cobalt we make from a cobalt 2 salt by adding ammonia and oxidizing it by hydrogen peroxide or by air, giving rise to corresponding hexaamine cobalt 3 complex, and that hexaamine cobalt 3 complex is a diamagnetic complex. So, just looking at the corresponding magnetic property, we see that the splitting is such that it only prefers the corresponding low spin situation, where all the 6 electrons will fulfilling the 3 T2G level, giving rise to a corresponding electronic configuration which will be T2G6. Then next the D7 situation, which is also true for cobalt-plus ion, the cobalt 2 plus ion. So, cobalt 2 plus ion will also have a 3 electron paramagnetism for the weak field ligand, and for the strong field ligand we have 1 electron paramagnetism. So, this is the situation what we basically encounter for making a compound which is initially cobalt 2 plus, like any cobalt 2 salt like cobaltous chloride or cobaltous nitrate, if we take in presence of ammonia, is basically getting oxidized by the O2 of air or hydrogen peroxide or any other mild oxidizing agents. We do not need any strong oxidizing agent to oxidize that, and this unpaired electron which is there if the cobalt center is in the bivalent state will be removed from the system, and the system will be oxidized, and this typical stabilization and the diamagnetic compound is getting stabilized in that way. Next is the D8 situation, which is very common for bivalent nickel. So, in the nickel 2 plus situation, what we find that we do not have any condition where we get that thing that in the on the left also, if we even if we go for these two conditions, we cannot change the number of unpaired electrons on the left as well as on the right. So, this is a situation where we cannot have any condition that we can put that is a low spin condition or the high spin condition. So, irrespective of the crystal field, we will have two unpaired electron for the bivalent nickel. So, these two situations are typically different for D5, D6 and D7, but the D8 system is completely different. We cannot distinguish between the high spin and the low spin complexes. Then we go to the other field, which is a typical tetrahedral field. So, as we have seen and we just jotted down all these informations for the octahedral field. Now, we know how we draw a particular tetrahedral field within a cube. So, this particular tetrahedral field when we draw, we have seen that a particular octahedral field or a octahedral crystal field, we have to place 6 ligands around the metal center. So, if at the center the red dot is the metal ion, we can have the ligands on the 6 faces of the cube. This is one from the front face and this is another one the back face. So, we have this particular octahedral complex. But what about the tetrahedron one? So, tetrahedron one we have to draw again within a cube and we place the same metal ion center at the center of the cube, but now we have the ligands. So, ligands will be there, 4 ligands will be there at the alternate corners of the cube. So, if we just recall back the shape of the different d orbitals, we will now face that in this particular case the 5 d orbitals are giving the sets the T2G level and the EG level, but the corresponding interaction for these for the tetrahedral field will be different, where the EG level will be stabilized and this will be labeled as E and the T2 level will be the destabilized one. So, we will have 2 low energy levels and 3 high energy levels, and G is dropped because this has no center of symmetry or center of inversion with respect to the corresponding crystal field. So, this will be the corresponding crystal field splitting when instead of octahedral field when we have a corresponding tetrahedral field. Okay. So, this we see here for the placement of all the orbitals. So, these two will be stabilized because these are not facing now directly, these green dots are the ligand dots, but in this particular case they are more interacting with those orbitals. So, this T2 set which is dyj, dzx and dxy, these 3 will be destabilized. So, T2 will be higher in energy compared to the E set. So, this is the situation. You see now these the black circles are the alternate corners of the cube, and if we consider all the d orbitals available and how they are interacting with each other. And more simplistic arrangement is that this is the metal ion center and x, y, z if we consider, and these are the approach of the 4 ligands on the 4 corners. So, this will be the crystal field splitting with respect to the corresponding spherical environment when all the 4 ligands are coming to split these 5 levels. So, this will be the corresponding levels, and likewise our delta O level, we have the delta T level for the separation is the total separation is delta T, which will be in the reverse order. So, it will be stabilized by 3/5 delta T and which will be destabilized by 2/5 of delta T, which is reverse of that of our octahedral geometry. So, again we can have the corresponding electronic configurations from D1 to D9. When we place the number of d electrons in these 2 levels, the number of electrons in the E level and the number of electrons in the T2 level. So, we get the corresponding electronic configuration with respect to the crystal field splitting. Now, how this magnitude of delta and particularly the more examples we consider for the corresponding delta for the octahedral field, how it is dependent on the other factors. The first thing what we have just considered is the corresponding nature of the corresponding ligand, we have compared that the fluoride as well as the cyanide. So, the cyanide ion Cn minus is the stronger ligand compared to fluoride. So, the electronically how we consider that thing when we encounter two of the compounds where we can have two different oxidation states of the same metal ion. So, the metal ion will also change the corresponding magnitude of this delta. So, this delta value which we experimentally we can determine by measuring the corresponding electronic spectra, because now we have two levels, as I told you that if we have two levels E1 and E2 for electronic transition, and if we move the electron from the lower level to the other level, we can experimentally determine the magnitude of that separation between E1 and E2. The same thing we can have with respect to the corresponding hexaco ruthenium 2 plus. So, ruthenium in the bivalent state is giving rise to a 19,800 centimeter invert separation with respect to the corresponding wavelength. That means that it can measure it in terms of the corresponding lambda value in nanometer. But if we move it for its corresponding trivalent state, you see is changing from 19,800 to 28,600 centimeter invert. So, for the same ligand system, that means the same hexaco species, our separation is changing with respect to the corresponding oxidation state. So, even if you have this, and if this is not stabilized, this particular species is not stabilized with respect to this ligand, then once it is going for the corresponding oxidation, you can change this oxidations environment, oxidized environment by other ligands, as I told you in case of cobalt. So, cobalt initially has the hexaco cobalt 2 plus, and which is ultimately oxidized to corresponding cobalt in the trivalent state, which is the hexaamine cobalt. So, the number of ligands and the geometry, as we just see that in octahedral case we have 6 number of ligands and the corresponding geometry is octahedral, and in case of tetrahedron the number of ligands surrounding the central metal ion is less. So, the corresponding splitting, that means delta T will be less than delta O, that will be there, and is roughly, if we consider for same type of ligands for the same metal ions in the same oxidation state, we will see that the delta T. So, delta T is about 4/9 of the delta O values. So, these are very weak. So, most of these cases when we see that this corresponding fluoride, chloride, bromide and iodide species, they are coordinating to the metal ion centers, they are basically giving rise to the corresponding tetrahedral complexes, where there is no such extra stabilization due to the corresponding gain in the CFSE values. So, the nature of the ligand, as I told you that you can expand the corresponding number of ligands more, and this has been taken from your CBSE book of chapter of coordinates and compounds, where we put iodide, bromide, chloride and fluoride, and in between we are bringing thiocyanate as well as sulphide groups also. So, the thiocyanate when binding to the metal center through nitrogen will come in between bromide and chloride, and the sulphide which is coordinating through sulfur only, which is bigger one and which is little bit soft also, which is having some strength which is less than fluoride, but greater than chloride. Then we occasionally encounter all the oxygen donors. Oxygen donors, you see that water is having some greater stabilization due to the splitting. So, the delta value for water will be higher than that of our hydroxide ion, though we consider that it has charge. Similarly, for the oxalate ion, it has charge, but the charge is not considering. These are the experimental quantities related to the corresponding delta values. So, the dipole of water molecules will interact and give the corresponding ligand field, which will be stronger than oxalate ion and the hydroxide ion. And these we already seen that the corresponding one for water, ammonia and ethylene diamine, EDTA will be in between. And lastly, these two things we will consider now, that why we can place these as the cyanide and the carbonyl complexes, that means the carbon monoxide can also bind to the metal ion in low oxidation state, that we will see very quickly. So, this give rise to the corresponding color thing, that means we see that how the crystal field splitting can also explain the color. This table is there in your book, and how we can read these values also, that when we have this compound, that is the pentamine chloro compound of cobalt 2 plus, so is the bivalent cobalt. So, the wavelength which is absorbed as 535 nanometer, which is in the range of yellow. So, we should remember that the Vibgyor thing and the Vibgyor wheel, the color wheel we should remember, and we can put the ranges for the corresponding range for the violet, indigo, blue, red, etc. So, this is the color which is absorbed, but we see the color of the solution. So, the complex color will be violet. So, this is the complementary color what we see for the corresponding compound for this complex. Similarly, if we change the chloride ion by water molecule and the oxidation state is also in the trivalent state, our value for this absorption is going to a lower energy value. That means, immediately you can know that one is absorbing at 535 nanometer and the other is absorbing as 500 nanometer. What does it mean? It is moving to the lower values of wavelength, that means, is high energy value. That means, the separation is bigger now, the delta value is bigger. So, when the delta value is bigger, it will absorb in the blue green region and the corresponding color of the compound will be red. So, definitely this will be the red. And if you go further, that means, all of them are substituted by ammonia, no chance of Cl. So, Cl is weak, that is why you can also get the information that Cl is weak, and for with respect to Cl is water is stronger, and with respect to water your ammonia is stronger. So, now we quantify whatever we have seen earlier, that we can replace those. So, if we get that, if we just have some idea that we can also be able to replace this chloride ion by water and water by the ammonia, but it is not so true for compound where we have something where two different types of ligands and pressure and more complications are there. But simply looking at the molecular formula of these compounds, what we see that the energy is changing towards the high energy values, that means the lower wavelength values, that means your delta values are changing. So, it is going to the range where the absorption of the color is blue and we get the corresponding yellow orange compound, and the solid compound is also nicely orange in color, yellow is orange in color for this compound, which is nicely crystalline solid we can get. Similarly, when we compare the fluoride as well as this compound, we have compared this is a cyano compound. So, hexacyano compound which is absorbing, you see, very close to the corresponding UV, that is the UV range. So, it is 350 is basically the starting point of our visible range. So, it is absorbing at 310 nanometer. So, this particular splitting is pretty high, and that splitting is basically is giving rise to the corresponding range, which is UV range. That we all know, we are just knowing the hydrogen spectrum, we are knowing in other chapter the hydrogen spectrum, and the separation between the 1s orbital and 2s orbital of hydrogen is also falls in this particular range, which is UV range. But what about the corresponding delta O values of the octahedral complexes? We see most of them are coming in the visible range, and this visible range is comparable to the series what we see in case of the hydrogen spectrum is the Balmer series, where we know that the Balmer series all the electrons transitions are taking place from the higher cells to the second cells. So, the Balmer series energy is comparable to the corresponding crystal field energy for these 3D elements. So, this and which is a very pale yellow, almost colorless. In case of the copper case, we have the corresponding this tetrahedral complexes, we can also get the octahedral complexes which is absorbing at some longer wavelength. So, which is red in color. So, again in respect to copper, these water molecules are giving rise to a weak field environment, which is red, and the compound is blue. And for the hexaaccord titanium, it is 495 nanometer and which is violet in color, and which is also characteristic. We can measure this 498 nanometer experimentally, that we just see. So, a light of wavelength we have to measure with respect to the transition from the E1 to E2, and that transition, if we just apply how this transition can take place with respect to corresponding hexaaccord titanium compound which is trivalent. So, just now what we have seen from your book is telling us that it will have some absorption as 598 nanometer. So, a range of light which is in the 500 nanometer, which is easy to remember that the 500 nanometer energy is sufficient to promote the electron from one level to the other, which is the ground level to the excited level, for one electron which is in the T2G level to the EG level. So, this transition can take place due to the light absorption of 500 nanometer, and we can also measure the corresponding delta value for that transition. So, how it looks like? We basically measure in one axis, it is the corresponding centimeter inverse we have plotted, but experimentally in a spectrometer we measure in the nanometer scale. So, this is the wavelength axis and this is the absorbance axis. So, that basically gives rise to the corresponding maximum absorption with respect to 498 nanometer, and that 498 nanometer is equivalent to 20,300 centimeter inverse is due to the transition from the corresponding level, which we see that the transition is excite. So, it is upper level is the Eg. So, Eg to T2G energy gap, or you can consider it as the transition when we move, when we promote this electron to the other. So, the transition is when we after some time it will come down. So, you can write this transition is also, and during absorption what is happens is the absorption spectroscopy, optical absorption we are talking. So, the during absorption the transition is taking from T2G to Ag, but after some time it relaxes from Eg to T2G, and energy gap in terms of the wavelength, which is 498 nanometer in terms of centimeter inverse, and in terms of kilojoule per mole also we can have, which is 243 kilojoule per mole. So, this particular information, that when we have a metal ion in solution, we see the color and we see the transitions very nicely. So, what about the thing which we see for the color of some gemstones, which is also there a part one page basically in your book, and you should read it nicely there, that when a particular light of visible range can strike a particular material which is the precious gemstone, it will absorb some color like your solution. The solution is absorbing one part of the color and it is eliminating or giving rise to the corresponding color which is complementary in nature. So, what is ruby? So, ruby has a very fine color which is red in color, and it absorbs all other wavelengths from the white light spectrum, only it is reflecting the red. That means, it is the complementary color which is coming out from that is red. So, that is why ruby is red in color, and ruby is nothing but is a gem quality corundum. So, corundum is nothing but our crystalline alumina Al2O3, but the color is due to some impurity which we call as the doping. So, 1% or less than 1%, 0.5 to 1% doping of the chromium 3 plus on the corundum can give rise to the chromium 3 plus electronic spectra for the corresponding color. What happens now in the solid state? All the oxides are your new ligands. So, in the solid state we can consider these O2 minus as our new ligands instead of water or hydroxide ion. So, these O2 minus will be now placing around the chromium 3 plus and will just distort the octahedral arrangement which was originally present for the alumina structure, because the chromium size is different from the aluminum size. So, doping is basically bringing some imperfection to the system, and it will slightly alter the corresponding absorption which we do not get for the corresponding hexachromium 3 complex. So, the new position of the O2 minus in the distorted form will be responsible for a typical coloration for this ruby gem. Another one is also sapphire, and is the chemical composition of both of them are corundum, but they exhibit different colors. This is due to the placement of the corresponding one which we get, that the composition is different. So, primary chemical composition may be same, but the corresponding impurities are different. So, what is purple in color? The sapphire one is purple, where we get instead of chromium in ruby we have vanadium, and it can come from different shades depending upon the corresponding distortion, and sometimes you can have some iron also present in this particular thing, and you can have the pale yellow to green in color. So, if both titanium and iron impurities are present together and a correct valence state, but what is the oxidation state of the titanium center and what is the corresponding oxidation state of the iron center, we will be able to get a deep blue color. So, synthetically also in the laboratory we can make nowadays the synthetic gem materials or the gemstones by knowing the corresponding metal ion which we can impregnate, and we get the corresponding coloration for all these things. So, beryl is another example. For emerald is a colorless pure mineral if it is pure only, but when chromium impurity like ruby is there, it will have a different color. So, if manganese is added instead of chromium, beryl becomes pink and name will be morganite. But if iron is present, this will be a different color and becomes an aquamarine. So, it is bluish in color. So, all these things are basically related to the formation of this beryllium in the aluminum cyclosilicates. So, what we talk now like your corundum, here also we have aluminum at the site, but is not in oxide lattice, but is a silicate lattice, cyclic silicate lattice we have, and we will try to replace this aluminum by chromium, this aluminum by manganese, and this aluminum by iron, because all are 3D elements. So, 3D elements can be useful to substitute this aluminum which is in the octahedral field having comparable size. So, the supply that replacement, this emerald will give you a green coloration for this when we have trace amount of chromium, and sometimes we can have the vanadium also. So, this impurity on all these gems will give rise to something which can give rise to the corresponding compounds. So, like your valence bond theory, the crystal field theory also have some limitation, but it can explain many more things which we cannot explain in case of the corresponding valence bond theory. So, here we the very basic assumption what we take, that we are considering these as point charges, but all these ligands, whatever ligands we can have, that cannot be the point charges. So, whatever is this we are talking here in this environment, these ligands which we are talking as point charges, but it is not that. If we have a bigger ligand, say if you have a iodide, iodide is also not a point charge, and if you have a very bigger organic molecule or organic moiety over there, so this will not be a point charge. So, this particular problem comes to us when we talk about the corresponding ligand as the carbon monoxide. Carbon monoxide is a well known ligand, and long back it was discovered that we can make some compound during the purification of nickel, the solid nickel which is in the atomic state, that means the nickel 0, when the gas valve contains nickel and the gas cylinder contains carbon monoxide, it is getting corroded due to the formation of tetracarbonyl nickel 0 compound. So, this is the corresponding deposition on the gas cylinder with that valve, and that valve will tell us this can form and in the 0 oxidation state. So, this is one aspect, that how we can tackle a corresponding compound where the nickel is in 0 oxidation state. Another one is the corresponding ligand which is not a point charge. So, if we do not consider that point charge, so the typical interaction what we are discussing so far about the corresponding charges for the positively charged metal ion and the negatively charged ligand, that the interaction we are considering as the corresponding interaction is purely electrostatic. That means the electrostatic interaction what we see in the rock salt like sodium chloride, but that electrostatic interaction is not present. What we see here, that if we have some molecule like carbon monoxide or Cn minus, another example is also Cn minus. So, it will have some orbitals. So, those orbitals will have some lone pair of electrons, and this metal ion will also have some orbitals which are having some vacancy or field. So, there will be something where we can overlap of the orbitals from the metal ion and the orbitals of the ligand. So, this particular picture of the electrostatic interaction only picture is now slowly fading away. So, we have to consider some amount of covalent interaction. So, that amount of covalent interaction how we can modify in case of a typical complex which is like Ml6. So, what is that covalent interaction? Covalent interaction is nothing but the molecular orbital formation what we have seen, like that of the same formation of carbon monoxide molecule. How a carbon monoxide molecule can form out of that corresponding configuration like this Lewis dot structure for the carbon monoxide molecule from the atomic orbitals of carbon and from the atomic orbitals of oxygen. So, what we get at the end, we get the corresponding molecular orbitals of MOs of carbon monoxide. Now, the donor levels or the acceptor levels whatever we have on the ligand, now it is your ligand. So, this ligand will have certain number of molecular orbitals, and those molecular orbitals will now slowly interact with the atomic orbitals of this metal ion. But when we have this is also a picture what we will get like the formation of carbon monoxide if M on the left hand side and L on the right hand side. So, we can also draw some levels which will be your molecular orbital levels, like this one will be stabilized, another will be destabilized molecular orbital level. for the ML6. So, that is the more improved version of the crystal field theory for bonding picture. So, we will not be able to consider this as the corresponding point charges for the dipole only case, and which does not take into account of the overlap of the ligand and the metal orbitals. So, consequence is that why we can say that the carbon monoxide is a stronger ligand than cyanide, we will unable to explain that until and unless we consider that carbon monoxide is having some interaction with the metal center as in a covalent nature. So, we will go for a ligand field theory where we introduce the concept of molecular orbital picture for this, and the valence orbitals will be considered by involving the metal ion orbitals and the ligand orbitals, where symmetry adapted linear combination. SALC is nothing but you remain within the symmetry picture, that symmetry adapted linear combinations of those orbitals will give rise to the several molecular orbitals, and those molecular orbitals will give rise to types of bonding which can be sigma bonding and which can also be pi bonding. So, we can where we have the ligand as a single valence orbital directed towards the central of the metal ion, and the pi bonding when the ligand has the field orbital of the pi symmetry around the metal ligand axis, whether metal is can give you the function as a donor or the ligand can also function as a donor. So, this we see for a very good example, that the corresponding molecular orbital, detailed molecular orbital picture which is there in any common book, that what we see that these are the levels, and instead of writing these, that is the carbon which is having higher energy for this 2s and 2p level compared to this oxygen. So, when we have the total number of 10 electrons on carbon monoxide, we will having the placement of these as the 3 sigma electron and 2 pi electrons. So, the sigma electrons on having some character which is close to the carbon character, which will give rise to the corresponding sigma donation. So, the HOMO will have this particular picture, and this blue orbital which is on the carbon side, this is carbon and this is oxygen. So, this will be the donor orbital. Similarly, the LUMO, basically we can have two LUMO, two of them are of the pi character. So, these 2 pi character of this. So, the LUMO of this will be there. So, on the carbon monoxide side we can have this LUMO also will be there and available for bonding to the metal ion center or the corresponding metal in the zero oxidation state. So, this is typically the sigma donation, and that sigma donation will basically give rise to something where the carbon side of this will be bound to the corresponding metal ion. Just now what we have seen in case of nickel, nickel in the zero oxidation state interacting with the carbon monoxide. So, we will have 4 such bonds will be forming. So, the nickel carbon bond will be there. So, we can have 4 nickel carbon bonds in tetracarbonyl nickel 0 species. And if we consider this nickel is in the zero oxidation state, so we can have all the levels filled. So, you can have not a 3D8 situation, we can have a 3D10 situation. So, all the levels are filled. Still some of the orbitals which are higher in energy, or some of the molecular orbitals, really speaking some of the molecular orbitals will all be available which are high energy acceptor orbitals. So, high energy acceptor orbitals will be there which can accept the electron density, the sigma donation, if we consider from the carbon monoxide to those level for a typical one direction bonding. But at the same time, since the all the levels are filled on the nickel 0, if you have the orbitals, whether it is a typical atomic orbital, but we are not considering atomic orbitals now, these are the molecular orbitals on metal centered or molecular orbitals. So, the field orbital electrons, the orbitals now push the electron density to the empty molecular orbitals on the carbon monoxide. So, highest unoccupied molecular orbitals. So, the highest unoccupied molecular orbital, the HOMOs are available for accepting the electron density from the corresponding metal centers. So, this will give you one corresponding sigma donation, and this will consider as the pi acceptance. So, that is why the carbon monoxide molecules will be considered as the good pi acceptor ligands. We classify them pi acceptor ligands, and that pi acceptor ligands will give rise to some multiple bonding between the metal and the carbon center, and the interaction is pretty strong, and that strong interaction is basically responsible for changing the corresponding splitting between the levels and the splitting in the terms of the corresponding delta values what we are considering for the crystal field theory. So, the separation is very high. So, on the spectrochemical series, that is why the carbon monoxide is on the extreme right hand side. So, in the zero oxidation state we can have several such compounds, and these compounds are very good examples for the simple carbon monoxide as the ligand for these compounds. So, we have the nickel, and this nickel is coordinating to those CO which is tetrahedral in nature, and these tetrahedral COs are there, and this basically another CO. So, these 4 CO will be giving rise to this. Now, the stabilization. So, the stabilization we can consider a little bit with respect to the effective atomic number what we use for the main group compounds with respect to the 18 electron rule. So, 18 electron rule can also be applied to these species such that initially we should know what is the formula. So, this is the carbonyl compound, unlike your NiCN whole 4 2 minus, where this nickel is plus 2. So, if we count the total number of electrons, this will be 8, and this is giving rise to 4 into 2. So, 4 plus 5 is a 16 electron species. So, it is not 18 electron species. So, but it has some stabilization in a particular geometry, because we all know that in a particular geometry is for this is the square planar geometry. So, the square planar geometry in this particular environment it has the stabilization, but for the zero oxidation state this nickel will have now 10 electron plus the cobalt carbon monoxide is also providing 2 electrons. So, 4 into 2, so is 18 electron system. So, tetracarbonyl nickel is a 18 electron system. So, it has a stabilization. If we consider not 10, instead of 10, if we consider that another 18 electron from the whole series, it will be there for the effective atomic number for this will be 16 in that particular case also. So, not only nickel tetracarbonyl, you can also consider it for the iron. Iron is having some electron which is there, we know that the 8 which is atomic number of 26. So, 26, that means 8 plus 2 into 5 10. So, it is also 18 electron, this is also 18 electron. But the situation is that what you can have for this dimeric compound, this is also these two dimeric examples, which is the corresponding manganese dimer and the cobalt dimer, what is there in your book also. So, this is the last slide what I have taken from your book also, and you should also some idea about the stabilization. So, these are the 5 carbonyl compounds, these are the good example of your corresponding organometallic compound, though they have given as the corresponding carbonyl compound, where the carbonyl ligand is in the extreme right hand side of the spectrochemical series. So, this is 18 electron configuration, this has 18 electron and this has also 18 electron configuration. This chromium, because the chromium having the 6 electron and the 6 carbon monoxide can give rise to 6 into 2 12 electrons. So, this is also another 18 electron species. But what about these manganese? Basically manganese, when we see that manganese we get, so manganese is 0, so that will give rise to a 7 electron to you, and then around 5, that means we are not going for a octahedral situation. So, we get 5 for that. So, that is there. So, we get in this fashion. So, 5 of them. So, 5 CO. So, 5 CO. So, 5 into 2, so is equal to 10. So, altogether we are getting a 17 electron species. So, this 17 electron species is not stable. So, if it can get something where we can have some bonding with another fragment. So, this is one part. So, left hand part of this, if we go for another part like this MnCO whole 5. So, due to this manganese bonding, we have to consider 1 electron, because it is made up of 2 electrons. So, this manganese bonding can contribute another electron. So, this will also be 18 electron. So, that basically gives rise to the corresponding stable species, which is 18 electron in nature. Similarly, for the species like CO2 CO whole 8, so that will also give rise to the corresponding counting, and all the time we should have some idea that how many carbon monoxide are there. 5 will be as monodentate and no such as the bridging groups, and 1 as the metal bonding. Similarly, for the corresponding cobalt system, we can have the bridging carbon monoxide, because this can also function as a very good bridging group. But considering the number of electrons for this particular one, we can also consider the bond. So, this will also have a cobalt-cobalt bonds, which will consider that extra electron, giving rise to a corresponding 18 electron configuration for that species. So, all these compounds, whether we have the 3 mononuclear compound nickel, iron and chromium, or 2 dinuclear compound the manganese or the cobalt, because in this particular case we have the cobalt-cobalt bond. Further you have the corresponding bridging, because the number of cobalt centers are less compared to your manganese compound. So, this is bridging, because the all the centered, because the left hand cobalt center and the right hand cobalt centers are octahedral in nature. So, all these 5 electrons basically are stable, and we can have some idea in relation to the 18 electron rule. So, if is something is not known, so F is unknown, and your ligand is also tell us that is the carbon monoxide. So, how many CO we can accommodate around the metal center is easy to decipher, easy to identify from applying this 18 electron rule, whether it is nickel or iron or chromium or a dimeric species, by looking at the 18 electron configuration with respect to all these species, and that stability is basically gained out of that, and we can have some idea that it is not a simple example and you have to memorize everything. The logically you have to think that 18 electron configuration is preserved in all these species, and the available number of carbon monoxide is there. So, definitely if M is cobalt, your carbon monoxide number is 8. Okay. Thank you very much.